All right, so we're looking at number 63 here from the um, uh, Momentum Energy Extra study questions, right? And, we've got like some sort of pellet here, okay? And it's placed in the barrel of a gun. It's propelled by a spring, force constant 50 newtons per meter. It has been compressed 20 centimeters. This barrel, right? And it's been uh, then released, right? And now our goal here is to calculate the velocity of this pellet after it's been shot, essentially through this method, right? And essentially, what we're looking at is we're looking at the idea that our elastic energy here, it just ends up becoming kinetic energy immediately, right? And so we're thinking about this pellet here, or this thing, and it's on a spring. Here's the pellet. It's been compressed a certain amount, and then when you let go of it, all of a sudden it has a velocity, okay? And our goal is to say, all right, well, here we've got some initial energy, and here we've got some final energy. And it's kind of like after it's been just left this spring here, okay, then we kind of pause the question and we say, okay, well, what is the velocity that that thing has? Well, as it turns out, the spring energy that the spring had gets fully converted over, due to the law of conservation of energy, over to kinetic energy. So this initial energy that we had should equal this final energy due to the law of conservation of energy. Well, the initial energy that we did have is equal to the spring energy, so elastic, and then we've got the kinetic energy, right? Is at your final scenario here. That's the law of conservation of energy. So the spring energy becomes kinetic energy. Formula for spring energy is 1/2 kx squared, and the kinetic is 1/2 mv squared. And if we take a look at what these things are, this is, well, not the mass. Over here we've got the mass of the. Sorry, this is the spring constant right here. Over here, we've got the mass of the pellet. Over here, we've got the distance that the spring has been compressed. And then right there, is the velocity with which the pellet leaves. Okay, and so we're just going to go ahead and solve for that. All this other information we have. We have the spring constant. This is K. Okay. We have the compression distance, which is this, and we've got the mass right here. Okay, and so what we can do is that, right? Go ahead and solve for that. Oh, it turns out actually that these 1/2s can cancel. I'm going to divide by the mass, so I'm going to get K x squared over m equals v rooted. Okay, that's going to be our algebra. And once you plug everything in to here, your K is 50. Your X is 20 centimeters. So you want to use 0.2 because you're using meters here. And then your mass is 5. It's 5 grams. So it's actually quite small. And so let's actually kind of take care of that. So that's 5 grams is 5 1,000ths of a kilogram. So it's going to look something like that. All right. And then once you root this, apparently what you get is around 20 meters per second there. Okay. All right, now we're looking at number 68 here, and it looks like from our drawing here, we've got a 4.5 kilogram block that's moving along at 2 meters per second. It comes in contact with this sort of board here that's attached on a spring. The question is what will the maximum compression of the spring be? So this thing is going to push the spring in, and at some point it'll stop, and then we pause. We again hit pause on the question. We want to know how much has that spring been pushed in right here, right? And so, in a way, this is a bit of the opposite question that we had the last time. Instead of the spring pushing and giving kinetic energy to the box is pushing on the spring and giving elastic energy. Its kinetic energy is turning into elastic potential energy that the spring then has. Okay, and so let's go ahead and take a look at this question. So a linear elastic spring can be compressed 10 centimeters by an applied force of 5 newtons. Let's first take this first statement here. Excuse me. I'm gonna buy some stuff. Let's first take that first statement there, and we're going to go ahead and analyze it. It says that the spring can be compressed 10 centimeters by a 5 Newton force. Well, what they're telling you here is that Hooke's law, right? The force on a spring is equal to K X, essentially. And what they're basically giving us here is the force and how much it's been compressed, okay? Where X is the compression distance of the spring. And what that's basically telling us, this is like a roundabout way of giving us the K value of the spring, right? And so if you do a little bit of algebra on this one, you find that K equals force applied on the spring for a certain distance. All right. And that'll give you your K value, right? And so what did we have? It was the force was 5 newtons, and the distance of compression was 10 centimeters, which is a tenth of a meter, 0.1 meter, and it looks like we're getting 50 here, newtons per meter, right? And that's going to be our K value, right? All right, that's going to help us in part 2, which is now a 4.5 kilogram crate of apples moving at 2 meters per second here. It collides with the spring as shown, and then now we're going to go ahead and answer that compression distance. So what we're looking at this point is we're looking at something like the 1/2 mv squared equals 1/2 k x squared. This is because the kinetic energy will become elastic potential energy, right? That's an F. I should have written K here for the kinetic energy. All right. And so there we have it. Oh, look at that. Our 1/2s cancel again. And now I'm actually solving for the compression distance, which is this X variable here. So if we do a little bit of algebra, I'm going to pass over the K, and I'm going to get rid of this square root, and it turns out I've got mv squared over K equals my compression distance rooted, or no, well, I root that side there. All right. And so as it turns out, this is the mass of the crate, or 4.5. My velocity that the crate hit with is 2. All right. And we've got, what else do we have here? K, oh, that's 50. That's from up here. And we go ahead and root all that. And apparently when you do all that stuff, you end up with 6.6 meters. So that's going to be your how much the crate sort of pushes the spring with. You know what I mean? And that's what we're looking at there. All right, so now I'm going to go ahead and advance to the next question. A spring bumper whose force compression relationship is F equals 50x is compressed 0.2 meters. All right, so what we're going to look at here. So part A is asking us to determine the potential energy stored in the spring at that compression. Okay, so essentially, in order to look at that, we first need to know the K value of the spring, right? And again, this is they're messing with us here, and they're giving us the K value. The K value here is 50 because they're saying that force equals Kx, and that's the rule. Force equals Kx, and so they're kind of basically telling us that K is 50 here. Okay. And, let me erase that. And so K equals 50. Now, we've got an X here, but they want to know what's the potential energy in part A here. Well, the elastic potential energy is equal to 1/2 Kx squared. And so it's basically just going to be 1/2 times 50 times 0.2 squared. Okay. And after you do a little bit of math on that one, it looks like we're getting 1. Huh. That's kind of fun. 1. And the units for that would be joules. Okay, so now part B here. That's how much energy is stored in the spring. It's 1 joule currently. All right. Now in part B, the spring is compressed a further 60 centimeters, right? A further 60. What will be the change in elastic potential energy here? Okay. And so basically you want to know, all right, well, what's the elastic potential energy currently? And what was it before? Well, we just know that the way that I'm reading this is it just had 1 joule of energy stored in it. And now we compress it a further 0.6, right? And so I'm basically going to figure out, well, what's the elastic potential energy at this, which is going to be, a further 60. A further 60. So that means it's now currently at almost 80 centimeters, right? And so what we can do here is we can calculate this as well. All right, so we calculate that and we get 16 joules. All right. And so that's how much joules it has currently. All right. 16 joules of energy. At 20 centimeters, it had 1 joule of energy. And now the change in elastic potential energy is the difference between these two guys, right? And so we're talking, it's going to be a total of 15, right? So the answer to part B is going to be, 16 joules. Well, let me write it out. It's the change in elastic potential energy is kind of what they're asking for, is elastic energy final minus elastic energy initial. So this final is tagged to the energy that it had at 0.8. The initial is tagged to the energy that it had at 0.2, right? And so we're basically going to be taking 16 joules minus 1 joule, and we're going to end up getting 15 joules. So it took an extra 15 joules to push that thing. All right. Now, a zero point 0.4 cart is placed against the compressed spring now on a horizontal frictionless plane, and the system is then released. With what velocity will the cart leave the spring, right? So we're looking at part C here, right? We're kind of doing this guy. So over here, I'm going to go ahead and write the results for this. It's part C. Now, basically what's happening is we know that there is currently 16 joules of energy stored in this spring, right? From the way I gather it, they pushed it to 0.2, right? And then they pushed it to oh, shoot. I actually messed this up. This guy right here, it says that the spring is compressed not a further 0.6, but compressed further to 0.6. Okay? And so, guys, everybody, this is actually incorrect. I need a 0.6 right here. I read that incorrectly. And so let me just quickly pause this and readjust these numbers. Okay, so we fixed that up. Sorry about that. So it was supposed to, I read that wrong. It's the spring is compressed further to 0.6. I completely read that backwards. So let's recap what happened here. They compressed the spring to 0.2, and then they compressed it to 0.6. So at 0.2, it had 1 joule of energy stored in it. At 0.6, it had 9 joules of energy stored in it. And now the change in energy is 9 minus 1, or 8. Okay, so now in part C, it currently has 9 joules of energy stored in it, right? And so we're basically looking at the idea that energy is now going to be converted into kinetic energy. And so we're looking at the law of conservation of energy. So the elastic energy gets converted into kinetic. And so we've got our 9 joules gets converted into 1/2 mv squared. And the question is what will the velocity be of the spring when it leaves the cart? And so I'll go ahead and multiply by 2, divide by the mass of that cart, and do all that stuff. Okay. And so we're going to go with this. So 9 times 2 over mass equals velocity. And we're going to root that. And so, what's our mass? Might as well go ahead and put that in there. Our mass is 0.4. Okay. So here's my 9 joules, and so forth. Do a little bit of a little bit of calculating on this. Hang on a second. We get 6.7, apparently, somewhere around there. Okay. All right, one more question here. A steel ball is moving with a velocity of 2 meters per second, strikes a second steel ball. The collision is a glancing one, causing the first one to be deflected at an angle of 30 with a speed of 1.5. Determine the velocity of the second ball after the collision, giving both its speed and direction. Okay, so here we've got a glancing blow scenario. So we've got one ball, and then we've got another ball here. This guy's coming in, right? And we know that it's got a 2 meters per second. Let me zoom in on this. This is ball A, we'll call this, right? Let me make this ball a little bit nicer. Ball A, right? And this is going to be ball B, okay? And then that's basically before the collision. And now after the collision, here's a collision, boom, 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 and bang. Ball B goes down that way. Ball A maybe flies up that way. Okay. Point is, we're not real sure if it's like, we're not real sure, right? What's going on here. So, but we do know that these guys have components, each of these velocities, okay? And so what we're going to do is we're going to break those components up into their particular values, and then we're going to essentially try and conserve the momentum in this question, right? So basically what's kind of happening here is all of this momentum right here should be equal to these two momentums here, because our sort of horizontal momentum is conserved, right? So that red vector should add up to both of those red vectors. My diagram is clearly not perfect, so but those two vectors add up to those two other vectors. That one, these red vectors. Okay, and I want to mention though that it's the not the velocity that's conserved, but it's the momentum that is conserved. All right, and I'll mention that again a little bit later on. Let's see if we can get another color here. We're going to go green. All right, there's green. These vectors here, as it turns out, should add up to each other. Now, why is that? Or they should be equal to each other. Why is that? Well, because the momentum in this section of the question, the vertical momentum is 0, and so therefore the vertical momentum over here should also be 0. Okay, and so because we conserve momentum, so I've got no vertical momentum in the left hand picture, right? Which is this one, okay? And so I should have no vertical momentum in the right-hand picture as well, all right? So that being said, let's take a step back here and read again what information they've given us here. Okay, so looks like we've got the first ball has a deflection angle of 30 degrees. So I'm going to go ahead and write 30 degrees here, and right in here, 30 degrees. Okay, this angle is unknown, so I'm going to call it a theta. All right, and it looks like we've also got a 1.5 velocity here. That would be this one, ball A, 1.5. 1.5. Okay. Now, I want to mention, though, again, that these are the momentums that are conserved, all right, not the velocities. So really what I'm going to do here is I've got a half a kilogram here, so I'm going to multiply this guy by its mass, so 0.5 kilograms, all right? Why am I doing that? Because basically it's the momentum that is conserved, so 0.5. And that way I'm basically turning this black vector into a momentum, right? Over here, down on the bottom, this is a velocity that I don't know, and it should be multiplied by the mass of ball B. Well, the mass of ball B is given at 30 0.3 kilograms. Okay, so I'm going to go ahead and do 0.3. Therefore, what I've essentially done here is I've made both of these vectors into momentums. Okay, this guy over here, on the other hand, I'm going to change him into a momentum as well. And so I'm going to go 0.5 because this is the mass of ball A, right? That doesn't look like a 5. Let's make that look like a 5. All right, there we go. Now everything here is a momentum, all right? Everything here is a momentum because it's a velocity multiplied by a mass. So the velocities are here in blue, and the masses are here in yellow. All right. And now let's go ahead and take a better look at these green and red vectors as well. All right. This green vector, according to our trigonometry, is actually equal to 1.5 times 0.5, which is the hypotenuse of this right triangle, times the sine of 30 degrees. Okay, that's that green vector there, right? Actually, I should have written that in green, but I didn't. I'll write this next one in green. Now, this green vector down here, the bottom one, the one facing south-ish, or down, let's say, is going to be equal to v. Well, we don't even know the velocity, so we'll just write v, and we'll multiply it by 0.3, okay? And we're going to multiply it by the sine of, an unknown angle. We don't know that angle. Shoot. Okay. But remember what we said earlier. We said earlier that these two vectors here, this green vector and that green vector, should be the same because remember there's zero momentum, vertical momentum in the y direction. So momentum initial y is 0. Okay. So therefore, momentum final y should be 0 as well. So therefore, these two guys must add up. They must cancel each other out. They must be equal because one's facing up and one's facing down, right? So I'm going to go ahead and write that. I'm going to say that those two guys are equal. So I got V times 0.3 sine theta is equal to 1.5 times 0.5 sine 30. Okay, so we'll keep that guy in our back pocket here. This is the y direction, right? And now in red, remember what we said before. It's in red. This is now going to be happening in the x direction. We'll write this maybe down over here. In the x direction, it's this 2 times 0.5, or the momentum 2 times 0.5. That's our x momentum initial, should equal those two red vectors, okay? Oh, but those red vectors are, this red vector, this first top one, the upper red vector, is going to be 1.5 times 0.5 times cosine of 30. 1.5 times 0.5 times cosine of 30 degrees. And that other red vector is going to be v times 0.3 times the cosine of, another unknown angle. Okay, well, it's okay. We'll be all right. We can solve for these things. And now we're going to basically do a little bit of algebra here and solve for this stuff. All right, let me expand this out a little bit. All right. All right, so basically what we're looking at here is a weird scenario where we've got a V and a V, and we've got a theta and a theta. Just highlighted those guys. So we've basically got two equations with two unknown values. And oftentimes what you can do here is sub one into the other. All right. And so what I'm going to do here is there's a couple of options here. I can solve for v in this green equation and then plug it in over here, and it's going to bring a sine with it, right? The sine of theta. And that's actually going to be interesting because sine of theta and cosine of theta, when you put them together like this, they could end up turning out to be something like a tangent or a cotangent theta. So let's go ahead and do it that way, right? So basically, I'm going to solve for v, and I'm going to say that v is 1.5 times 0.5 times the sine of 30, which is 0.5 as well, over the sine of theta times 0.3. 0.3, I forgot that 0.3 there. And now, if you kind of calculate all this, it's just going to end up being, sine of 30 is a half, times another half is a quarter, and divided by a third, though. And, well, that's 15. That changes that to a 0.5, a quarter of a 0.5. Let me type this all out here. All right, so yeah, it looks like we're getting a 1.25 over sine of theta. And we're going to take that and plug it into here. And so I'm going to go ahead and take this red equation and I'm going to, crunch this thing down a bit. So we've got a 0.5 times 2. Well, that just turns out to be 1. 1.5 times a half is a 0.75 times the cosine of 30. Well, that's the square root of 3 over 2. We might want to actually just go ahead and put that as a decimal a little later on. Plus v, which is 1.25 over sine of theta times 0.3 cosine of theta. All right, that's what we're looking at basically. I just stuck v in there. Now, we've got these two thetas, and you might think, well, this is going to be annoying, but turns out it's actually not going to be too bad at all. Let's take a look at this. So I'll subtract over this thing, and so I'll get 1 minus 0.75 times the square root of 3 over 2, which is, I guess, is 0.375 or something like that. I'll just leave it as a 2 here. Okay. That's passed over, right? This equals the 1.25 times 0.3, right? And so that guy gets passed over as well. And that's a 0.375 as well, right? So 0.375. And it leaves me a cosine theta. And you can push this sine theta right over there, okay? And as you may remember, cosine theta over sine theta is the cotangent of theta. But I'm going to have to get rid of this 0.375 as well. So it's basically this thing, which is 1 minus 0.75 root 3 over 2 divided by 0.375 equals cosine theta over sine theta over sine theta. And there we go. We've got our solution here. Now, I know that cosine theta over sine theta is cotangent, but I also know that sine over cosine, that's sine over cosine, so which is basically the reciprocal of what we have here. That's not cotangent, but that's tangent. So I'm going to reciprocate both sides, and so I'm going to get a 0.375 over 1 minus 0.75 root 3 over 2. I just reciprocated this side, which allows me to reciprocate this side, which is sine over cosine. And it turns out sine over cosine is actually equal to tangent of theta. And now, if I go ahead and do a little bit of algebra or inverse, I'm going to go ahead and fly over into this direction here. I'm going to say that theta is the tangent inverse of this stuff here. Okay, go ahead and throw that into there. All right, and if you do a little bit of algebra on that, or a little bit of solving, plugging it into the calculator, apparently what you end up getting is about 47 degrees, right? So 47 degrees, right? I didn't, so 47 degrees. Okay, that is now the angle up here that we're looking at, that little blue angle. Okay, so hopefully you're kind of following along here. Question is, what's the velocity? Well, now that we know that that's 47 degrees, I'm going to take this green function here and I'll pass it over this direction. And now that I know that that theta is 47 degrees, I've got a nice little easy calculation here. And so let's go ahead and do that. So passing this over, I'm going to get the velocity is equal to the 1.5 times 0.5 times the sine of 30 over the 0.3 sine of theta. So 0.3 sine of, that happens, sine of 47 degrees. That's pretty cool. And there we have it. We just solve a little bit of that, and apparently you get 1.7 meters per second. This is a glancing blow question, right? So this is what's going to happen in these glancing blow questions, right? You're going to get your y component here, right? And your x components here. And you're going to have to do a little bit of, algebra to get those guys figured out. We got one last question to work through here. Let's check it out. A 300 kilogram space capsule is traveling in outer space with a velocity of 200 meters. In an effort to alter its course, it fires a 25 kilogram projectile perpendicular to its original direction of motion at a speed of 2,000 meters per second. Wow, that's fast. What is the new speed of the space capsule, and by what angle has its direction changed? Okay, so this is a pretty cool question. And so as it turns out, we've got kind of like almost like an explosion question here. So let's draw this out. We've got our little space capsule here. I'll just draw it like a pencil or something. And on the side of it, it's got like this 25 kilogram thing here. And it's traveling through space at 200 meters per second. Boom, boom, 200 meters per second. Then all of a sudden, this this green thing shoots down perpendicularly, okay, to its original direction of travel at 2,000 meters per second. What is the new speed of the space capsule? So this little ball or whatever that thing was shoots out there, okay, and there we have it. The space capsule itself, while this happens, will end up pushed that direction, right? So let me actually make a better picture because this picture isn't working out very well. So my space capsule is going to kind of continue forward and it's gonna have like a sort of a velocity that's moved up like that, whereas this guy has a velocity that uh, uh, is like that. Now, the way that I read this question is, does the little projectile also keep its forward velocity? In which case, it would have this 200. I would assume that this little projectile, which is, maybe I should make this little thing red or something. This little red thing here, right? It was shot out like that, but it also should keep its 200 meter per second forward velocity, right? And also, the space capsule itself should keep its 200 meter per second uh, velocity as well. Okay, and so let's go ahead and make that assumption. But let me actually let me think about that for a moment. All right, so I just kind of checked the solution here, and this 200, no, sorry, this 2,000 meters per second, it says that it's perpendicular to its original direction of motion. It's a bit confusing, or counterintuitive, but what they're intending here is that the thing, rather than like having your ship here, which is here, let me draw a nice ship here. Rather than having your ship, shoot this thing. Oops, sorry. Shoot this thing down, and then it sort of keeps its forward motion as well. They somehow actually manage to perfectly shoot it down such that it no longer has this 200 meter per second forward motion anymore, right? And so, I mean, that's the way that the person who wrote this question is interpreting it. All right, so um, as it turns out, this little red block here that's been shot down, they somehow managed to shoot it out perfectly perpendicular so that it loses its 200 meter per second forward velocity. Okay. That being said, right? Okay. With that being said, then the intention is that this momentum here that the ship has should be equal to this momentum, right? Plus, then we've got this momentum that the block has should equal a momentum that the ship has maintained, or gained here, for a complete now new momentum in that direction. All right. So you kind of imagine that the ship maintains its forward green momentum. Okay. And this new red momentum is sort of added on to it in the up direction because it shoots a block in the down direction. Okay. So the question is, well, let's just go ahead and figure out these momentums. All right. Well, this green momentum here is going to be the mass of the ship plus the block times 200. So this is 3,025, right? Because the red block is still here. So it's 3,025. 25, right? 3,025 times 200. That's this green horizontal momentum. And so basically we could kind of say that this is 3,025 times 200. All right. This thing here is 2,000, which is the velocity of the block, times the mass of the block, or 25. Okay, so that's, sorry, I'm doing these a little bit backwards. This is a velocity, and that's a velocity, whereas this is a mass, and that's a mass. Okay, but basically that just means that this red vector is also 2,000 times 25 as well. And so now this new purple vector up here, which maybe I'll kind of go with purple. Am I in purple? There's purple. This is now the momentum, the new momentum of the ship. Okay, and so we can kind of just go right triangle scenario here and figure out this using the we could use the Pythagorean theorem if we want. But what is the new speed, and by what angle has it changed? Oh, we want this angle, and so I guess it seems logical to use the tangent is going to be the opposite, or 2,000 times 25 over 3025 times 200. Sorry for mixing those up. That's again a velocity and a mass, and then a mass and a velocity here. And if I cancel a couple of these numbers and get a few things going on here, apparently this angle is going to be about about 5 degrees here. All right, so we're going to write that as about 5 degrees. Okay, that's how much it's been sort of shifted up by. Okay, now if we want to know the speed of this thing, we're going to go ahead and again analyze this right triangle here, and we're going to figure out this momentum, the magnitude of it. So I'm going to go ahead and go with the Pythagorean theorem. So we've got the P is, that's the momentum, is going to be 2,000, right, times 25, all of that squared, right, plus 3,025 times 200, all of that squared, and we square root it. That's going to give me that purple vector. Okay, it's going to give me that purple vector, but that's a momentum, right? And so if I go ahead and solve that, I think I'm going to have to calculate that through. Let me get that. All right, so calculated that. That's 60,706 kilogram meters per second, because that's a momentum. We want to. That's the momentum of the ship now. It's new momentum. This purple vector here. Okay, but remember, that's the momentum of the ship. They want to know the velocity of the ship, and so the velocity of that ship is going to be, well, we know that momentum equals mass times velocity. And so what we're going to be doing here is we're going to take this momentum and we're going to divide it by the mass of the ship to get its velocity. And so we're going to get the momentum of the thing divided by the mass of the ship is going to be the velocity of the ship. And apparently you get 200, around 202 meters per second there, right? So that was a bit of a doozy. That was a weird question. Remember, the way that they write this question out is that the projectile is shot such that they manage to shoot perpendicular to its original direction. Okay, so you kind of imagine if you're flying through the air in this ship, you don't shoot this projectile off such that it maintains its forward momentum. You somehow kind of push it a little bit, from your perspective, you actually kind of shoot this off a little bit backwards as well. Okay, and that's kind of how that question is addressed. All right.